the recording. Okay, so it's recording now. So our 5th week Zoom session is recording. Starting here in Module 4, we're moving to really what is the big goal for statistics and for statisticians, but not just for statisticians, but for those that use statistics in other fields, that is doing statistical inference. And so this definition is not the first time you've seen it. There's 2 modes of inference estimation, which is point estimation or interval estimation, and hypothesis testing. We looked at estimation first, in particular point estimation. Do y'all have any questions about point estimation? Okay. Then we briefly introduced the idea of an interval estimate. Basically, a point estimate for a parameter is too rigid. It doesn't reflect sampling error, but an interval estimate does reflect sampling error. And so we have this thing called a confidence interval, and we have a confidence level with the interval. That basically is a measure of the correctness of our interval. We don't really, in practice, we don't have 100% confidence interval. That wouldn't be realistic, but we can have 90%, 95%, and 99%. Those are common levels. Questions in general about confidence intervals before we get to the specific ones? Okay, so starting off here, we are doing statistical inference on a population mean mu, and there's several scenarios here. The first scenario is when sigma is known, and if you follow the notes here, and even in the text as well, you notice that this scenario is kind of fictitious because here we're assuming that we know the standard deviation sigma. Sigma is a standard deviation of the population, and we rarely know that. In particular when we don't know mu. So anyway, this is kind of it's a nice setting to start. We had an example there with this confidence interval for population mean mu. Anyway, I don't want to re-lecture, but I want to take some time for questions over this example. Is it okay? All right. This page was the derivation of the confidence interval. The point of this is for us to see mathematically where does the interval formula come from. And it all starts with the sampling distribution, which was an idea from the previous module, chapter, let's see, was that chapter 4? Chapter 4, the sampling distribution of the sample mean. And that was a starting point, and ultimately, after some algebra here, we got to a lower bound and upper bound expression, and that was the basis for our confidence interval. Any questions with this page? All right. This page here, margin of error, this is an important idea. It looks at the interplay between the width of an interval. Actually, this whole page here looks at the interplay between the width of an interval, the standard deviation of an interval, the sample size, the confidence level. Those are all related. And that ultimately in this page got to the point where we had a sample size determination formula. Questions with this page? All right. Here's an example, sample size determination. And then here is kind of an important question. Everything up to this point had assumed that we know the population standard deviation, which is not practical. So we move to a more practical setting here. Estimating mu with a confidence interval when sigma is unknown. Okay. So here we had two scenarios, one where the sample size was large and the other where the sample size is small, but the data comes from a normal population. And to generate one of those methods, I needed to talk about this new distribution, the student's t distribution. This function here, this function that I have listed here, I said it in the video anyway, I put it there just so we have a sense of where these plots come from. But the t-distribution, that function, let me back up, really we're not going to deal with that in any real way. We're going to look at the plots, the t-distribution plots, this bell curve. It's very similar to the standard normal curve. There's a relationship between the two. As the degree of freedom increases, the t-distribution approaches the standard normal. Do you have any questions about that, about the t-distribution? Okay, so back to confidence intervals. Let's see, the first scenario, what do we have? When sigma was unknown, a large sample scenario, and when sigma is, so the large sample scenario, but when sigma is known, or when sigma is unknown, but we have a small sample, we use the t-distribution here. So there's these two interval formulas, very similar in structure. One has a z multiplier, the other has a t multiplier. Y'all have any questions with these two formulas and the way they're set up? Example here, confidence interval for population mean when the sample size is large. And then here was an example, confidence interval for population mean when the sample size is small. Okay. By the way, this sort of scenario might be common for an exam where I would give you this kind of jump output, and you might have to compute the confidence interval from it. And maybe comment on the reasonableness of the underlying population being normally distributed. But any questions with this example? Okay. I haven't heard anything. I guess if somebody wants to type something in the chat windows, let me know you're still there. Okay. Thank you, Latrice. All right. Okay. Sample size determination. When the population standard deviation is unknown, that's what this section was about. Here we had an example for that. That wrapped up, page 13 was the last bit of notes that dealt with the confidence interval for a population mean. Do y'all have any thoughts, comments, questions on confidence intervals?
I do have a quick question. This is Elizabeth. Go back a couple of pages back to the t-distribution chart, I guess, back to where for the the small sample size, and you have that T sub alpha divided by 2 deal, where we multiply. Where do you find that T value? I've got the T chart in front of me. Yes, yeah. How do you find that T value? I understand how to find it in the Z chart, but not in the T chart.
Okay. So let's look at this example, this second example here. Let's see. So in this example, you're maybe asking the question, how did we get 2.1098?
Yes.
Okay. So first you have to identify the degrees of freedom. Now here I used the Greek letter nu. Sometimes the book has, and sometimes I'll say DF for degrees of freedom. But anyway, it's the sample size minus 1 in this case, which is 17 because there's 18 data points. But you get that number. First remember the degrees of freedom. And let's see, the T value, let me see if I can annotate a little bit here. The T value here, T sub alpha over 2, in this case, is my confidence interval. Let's see, my annotation's not, what's the confidence level here?
Hang on, I'm looking. No, I just see teen children. I guess I'm not sure. 95%.
Okay, good. So 95% confidence interval. So let's see. So that means the alpha is going to be 0.05, right? Alpha is 1 minus the confidence level. So if I've got a 90% confidence interval, then alpha here, so 1 minus 0.95, this pin, okay, so that's, man, 0.05. So my T value is T with a subscript of point, let's see, all this technology here, T sub 0.05, trying to draw a 0, then a 5, over 2. This is terrible. Can y'all see that?
Yes. So that gives you 0.025, right?
Right. It's almost better just to talk it out. It's strange. I can create videos and have clean writing with my stylus, but whenever I use Zoom and try to have a session anyway, so there's a lot of technical issues behind it. This particular technique's not working very well. So, but I would have let's see, T subscript 0.025. So you're looking for the upper 2.5th percentile on the T distribution. So if you go to table T here, if you go to table T, and get rid of all this. If you go to table T there, or table 2, I'm going to look for the value that has a right tail probability of 0.025. So I'm going to be in this. Does my cursor show up in this column here? Y'all see, does my cursor show up there? Maybe not, but it's the column with 0.025 in the heading, and I go down to degrees of freedom 17. And what do I have there? 2.110. Is that what y'all are seeing? That's not supposed to.
Yes.
2.110. Okay, what did I have in the notes?
Maybe I think 2.1098.
Yeah, I think what happened is I actually used a different table that had a slightly different precision than what this does in the book. But if you use 2.110, you know, that's very close to 2.1098. Anyway, so
okay, that makes sense.
That's why that's different.
Okay.
Other questions with confidence intervals? Okay, hypothesis test, the other way to do statistical inference. This is a little more, at least for me it was, and I find for most students it is a little, maybe a lot trickier than confidence intervals, because there's all these parts to a hypothesis test. The big picture is kind of the same. You want to do inference. You want to say something about an unknown parameter, but you're really saying something about statements or hypotheses about a parameter. And so anyway, so there's all this setup. There's a research hypothesis, statistical hypothesis, the null hypothesis, alternative hypothesis. Make sure you're clear on what those are in a given setting, and setting those up for a problem is important. I tell students that the claim that we want to test, that's what goes in the alternative hypothesis in terms of for statistical hypothesis testing. But anyway, there's a philosophy of hypothesis testing that assumes the null hypothesis is true and looks for overwhelming evidence to reject it and accept the alternative. In hypothesis testing, there are types of errors: type 1 error, type 2 error. Make sure you know the definition of both of those. We are protecting against a type 1 error when we choose the significance level or the alpha value in a hypothesis test. Questions about the null hypothesis, alternative hypothesis in general. We might come back to this in the context of an example, but before I move on past all these definitions, are there any questions with these terms and ideas? Okay, so in doing a hypothesis test, if you notice the way the book works problems in their examples and the way WebAssign prompts you for steps in a hypothesis test problem, it can be a little bit different. Here I put 5 steps down that are important, in that I might ask you to do all of these steps on an exam, and you notice throughout the examples here in the notes that I cover these steps early on, and maybe as we make our way through more hypothesis tests, I just do parts of these steps. But anyway, are there any questions with these important steps?
Okay, I have a question that might be kind of silly. Like all these steps, and like when you went through the notes and you went through them with us, like, I mean, I could see where you were going. I could look at those notes. I could get what you were going to do next. But like, for this is like totally new, I feel like, to most of us. And I mean, I feel like you're probably going to say, well, you're just going to have to study it. But I mean, is there like a trick to like I know it's just 5 steps, but there are so many steps within each of the 5 that sometimes I just feel like I'm mixing them up. I'm not really completely sure what to do next, or it's a little overwhelming. It's just like a big chunk of information that's one thing, and I totally get it and respect it and all that stuff. I'm just my question is like, for somebody like us, is there just what is your suggestion? I mean, is it just you're just going to have to learn it step by step and know, or is there an easier trick, or what?
Let's see. I don't.
And I know that's a
I'll
question.
say this. Yeah, I'll say this. In terms of exams, I'll prompt you for what steps I want you to go through. You know, I'll say in this hypothesis test problem, you know, give me the parameter of interest, and you know, what test statistic are you going to use, and what is its distribution. I won't. I'll prompt the important bits of the hypothesis test that I want to see. In terms of, maybe I'll say an encouraging statement is this method, this hypothesis testing method. This is the first time you see it, but we're going to use this technique throughout the semester. In other words, when we get to Module 5 after Exam 1, we're going to do statistical inference on 2 population means. And so we're going to have the same sort of steps to run the corresponding hypothesis test. And so the more of this you do, I think with most things, the better you'll understand it. I know this is very different than what was in Chapter 4 and then in previous chapters, and it's very different even in terms of what you see in a math course. But it's the statistical approach to the scientific method, if I could say it kind of in a nutshell. And so anyway, there's these different these steps involved. So I don't know if you want to hear. You may have not wanted to hear me say this, but working more problems, the more you work, I think the more it'll make sense. There's not a magic bullet with hypothesis testing for most students. You just work a lot of problems, and you've got the WebAssign, which really probably isn't enough for y'all to get the experience and the problems that you need, but it's just enough to kind of to keep you doing the material and to for me to make micro assessments along the way. I would work at practice problems that I have posted. I would work through examples that are in the book, and then a lot of the exercises at the end of every chapter have solutions posted to them, or at least answers posted to them at the end of the book. That's my recommendation.
Okay. Like I said, I know that was a loaded question, so I wasn't really trying to put you on the spot. But
no,
I appreciate it.
Well, yeah. I mean, it in some ways it is what it is, but this technique, while it's new, and this philosophy of doing mathematics and kind of quantitative stuff is probably new to most of to a lot of students in this class, it is important, and it will be used throughout the semester. So you kind of learn it now, and you'll learn it better and better as the semester goes along. And there won't be this module 4 in this sense makes it a difficult module compared to later modules, because hypothesis test is a new thing, and just the philosophy and the structure behind hypothesis testing in general is complicated at first. And so some good news is that we'll use this stuff over and over throughout the semester, and you won't have this sort of, how do I say it, new kind of inference that has all these important working parts. You won't have this thrown at you in a given module like you have in Module 4. Y'all may tell me I'm lying later in the semester, but that's kind of how I view this hypothesis testing within this module. Other questions before we move into the specific testing methods? So the first scenario we looked at was a test for mu when sigma was known. And again, this is a fictitious scenario, but it is a good place to start. And it's analogous to this setting for the confidence interval when you assume that you know sigma as well. And so then here was an example, and I know these examples, this one took a while to work through. But anyway, so we went through all the details on this example. Are there questions with this example? Do you see where the pieces come from? Any questions with this example?
Dr. Riggs, it's Anna.
Yes.
I had a question.
Hello.
Hi. I had a question just about the p-value approach. I guess I was trying to implement that in one of the homework questions, and we can deal with that when we get to the homework. But I was just kind of wondering, I guess I got confused between the t-value and then the number that I'm supposed to plug in where it says z is greater than or equal to 2.85.
Right.
So that was the number we got from our observed test stat.
Right.
And I think that I was just calculating the t wrong on the homework. But
the probability?
Is that what t is?
Yeah. So where it says p-value, now sometimes the book will call it the observed significance level.
Okay.
But I think in WebAssign it calls it the p-value.
Yeah, it did.
And so in this setting, in this particular problem, the probability, it goes back to, okay, our test statistic is a z, and what's the distribution of z? Well, it's standard normal. And that's the picture I have drawn out here, that normal distribution. And so I'm trying to find an area, or the area under the curve to the right of 2.85. And so I shaded it there. You can kind of see it. The area under the curve to the right of 2.85 is, so I had to use table N to get that. Do you see, or the standard normal table? So I had to find the area under the curve to the left of 2.85. So if I use the normal distribution table if I look at 1 minus that. So 1.85 has a left area of 0.99678. And so you subtract that from 1. Did I look at that wrong? 2.85. 9978.
Correct. Mm-hmm.
9978. So 1 minus that is 0.0222. A couple of things about the p-value. It involves the probability of your test statistic, and so you have to know the distribution of your test statistic. At this point within this module, we either have a test statistic that follows a standard normal distribution. We call that the z-test statistic, or we have a test statistic that follows the student's t-distribution, or sometimes we call that the t-test statistic or the t-test.
Okay.
So you're going to have to work with either one of those distributions to get the p-value or to approximate the p-value. Sometimes you have to do that. If you can't get it exactly from a table, you can approximate it. So anyway, I don't know if I got to your question to begin with.
Yeah.
I'm
sorry, go ahead.
I would say, do you see why it's the probability that z is greater than or equal to 2.85?
So I know we got the 2.85 from the observed test statistic.
Right.
And I understand that formula.
Okay. It's a greater, so you notice I've got greater than, right? We've got greater than here. Instead of less than or equal to, that's driven by the alternative hypothesis. And so let's see if you look at the alternative hypothesis here, I've called this a right-tailed test where it's got mu is greater than the null hypothesized value of 43.5.
Right.
And so 43.5, that went in our test statistic. But anyway, so it's greater than that. That's what the greater than comes into the p-value computation. If it was a left-tailed test and we had less than the alternative, we would have a p-value that's less than or equal to. Now, I mean, that's kind of the rule, but the reason is because the p-value, the definition of it, is the chance or the probability of seeing your statistic or one more extreme. Now, our statistic that we saw in this example was 2.85, but more extreme, what do you mean by more extreme? Well, is it more extreme in the right tail of the distribution or the left tail of the distribution? So the more extreme is always in the direction of the alternative. So here, the alternative is greater than, so the more extreme part
is in the right tail.
Is going to be greater than. So it's just saying, hey, we've seen this test statistic, 2.85. What's the chance of seeing something larger than that, assuming the null hypothesis is true?
Okay.
And that chance here is really, really small, 0.0022. And so because we have seen, that tells me that 2.85 is a rare observed test statistic if the null hypothesis is true. In fact, it's so rare, I'm going to reject the assumption to begin with that the null hypothesis is true.
Okay.
It'd be kind of like if I told y'all I had a fair coin, that means the chance of a head or a tail is the same. And if I flipped it 2 times and I got 2 heads in a row, you'd still believe that it's fair.
Mm-hmm.
But if I flipped it, say, 4 times in a row, and I got 4 heads in a row, you might start to doubt that. If I got 5 heads in a row, you really might start to doubt. If I got 6 heads in a row, your doubt would just increase more and more. That my assertion that the coin is fair, you might start to reject that when I get 5 or 6 heads in a row. The reason is because although your mind isn't directly doing it, what's going on is you're thinking about the chance of seeing 4 in a row is somewhat rare. 5 in a row is rare. 6 in a row is really rare. And so I'm going to reject the assumption up front that there's a fair coin. So that sort of thinking is what drives hypothesis tests and how we view the p-value and make a decision from it.
Okay.
Other questions with this example? Okay. In this scenario here, we move again. This last question on page 18 motivates a hypothesis test for mu when sigma is unknown, because that's the more common situation. Now, there's two scenarios here. Again, a large sample size scenario and a small sample size scenario, but where the data comes from a normal population. So we had a large sample. I've sometimes called this a z-test. And then we had the small sample t-test. If you look at the structure of the actual test statistic, this structure here And this structure, I don't think I need to do all this. Here, those are the same, right? One has a Z in front, but the other has a T in front. The ratio is the same, but dependent upon the situation, if you have a lot of data or a small amount of data, but you know that your population, or you have good evidence that your underlying population is normal, that governs, should I use the standard normal distribution in my test statistic or the T distribution in my test statistic? And you know, when the sample sizes are large, they're both the two methods are very similar. They yield very similar results. But when the sample sizes are small, the t-test is often what's called for. Anyway, so there's those two tests there. Here was an example of a t-test, right? Because we had a small sample size here. And in this t-test situation, we went through, I think, all the steps in this example. Are there any questions from this example here? Do y'all want me to walk through this example slowly and y'all going to ask a question out of each step?
Sure.
Okay, so a machine produces ball bearings. It's the nominal diameter is 1/2 inch, and so we are testing the idea that the average diameter of all ball bearings from this machine is 1/2 inch. So we take a sample of size 10 to test that idea. So thinking statistically about the problem up front, the parameter of interest is mu. It's unknown. We would have to observe every ball bearing or the diameter of every ball bearing to know mu, but we only have 10 ball bearings in front of us. So mu is unknown. We want to do inference on it. The question here is, can we conclude at the alpha equal to 0.01 level that the mean diameter is not 1/2 inch? And so that question, it didn't say, can we conclude that the mean diameter is greater than 1/2 inch? It didn't ask, can we conclude that the mean diameter is less than 1/2 inch? It just said, can we conclude that the mean diameter is not 1/2 inch? So it's kind of ambiguous in terms of which direction. And so that forces the alternative hypothesis here in step 1 to be that mu is not equal to 0.5. So with this kind of alternative, we call this a two-tailed test. If that's the alternative hypothesis, then the null hypothesis has competing. It has to be that mu is equal to 0.5. So that's step 1. Step 2, what's the test statistic and the distribution? Well, the test statistic that we would use in this scenario would be one that follows the situation, the problem at hand. And so we have a small sample size. The population standard deviation is unknown, as it usually is in real world situations. We got a small sample size, so according to this kind of scenario here, we can't use scenario 1 because we don't have a large sample. We use scenario 2. But in scenario 2, we have to have some evidence that our data comes from a normal population. And so what I've got here is the QQ plot from JMP, and it's pretty close to linear. There's not any points that are falling grossly outside the bands there, those dashed bands that might indicate some non-linearity. And anyway, so we went ahead and went with the assumption that the data comes from a normal population. And so this t-test statistic is the one that's chosen here in step 2. The t-test statistic, and it follows, of course, a t-distribution with 10 minus 1 or 9 degrees of freedom. Step 2. Step 3, the significance level, that's basically chosen for us up front, 0.01. The rejection region, I have to split the significance level.
Can I ask a question real quick?
Yes.
Can I ask a question real quick? So for testing purposes, so if you're asking what type of distribution, you're basically asking for and sorry if I'm being repetitive here, but you're basically asking for either a T distribution or a Z distribution, and we would base that off of our sample size?
At this point, yes.
Okay.
Yeah.
Okay, go ahead.
But also, that's a good question. But also with the understanding that if your sample size is small, you can use the T, but you've got to be pretty sure that your underlying population is close to normal or symmetric, and a QQ plot helps with that. A problem in the book may say you may assume that it's the case, and frankly, when I see WebAssign do problems like this, or even problems in the book, when they just give you a small sample scenario and they don't say anything about the underlying population being normal, I don't really like that kind of problem, because to use a T statistic, that's an assumption that we need to be mindful of, and at least told that it's reasonable or have some way of checking it. But generally, yes, doing inference on a mean mu when the sample size is small, the T test is going to be the approach, and if the sample size is large, the Z test is probably going to be the approach, or it's going to be the approach.
Is it going to be something totally different when we have a not normal population?
Good question. Yeah. So the early part of next week is the last bit of Module 4, and it deals with the situation when you don't have a underlying normal population. And so what's typically done is, if the sample size is small, let me back up. If the sample size is large, and for us, we'll just say large is 30 or more. If the sample size is large, you really don't have to check the shape of the underlying population, because the central limit theorem kicks in and everything's okay in terms of distributional results. That's what the scenario 1 basically is. The sample size is large. But if the sample size is small, like you say, what if we don't have a normal population? If you don't have a normal population and the sample size is small, for us, we're going to look at a situation where we do inference on the population median as opposed to the population mean. And there's a different technique called the sign test that's at the end of this module that deals with inference on the population median.
Okay. Thank you.
Okay.
Yes.
Yeah.
Thank you.
Step 3 here, significance level. Alpha is split in 2. So alpha 0.01 divided by 2, when you divide that by 2, you get 0.005. So that's the right tail area and the left tail area. Notice I've got a two-tailed rejection region, which is why this is called a two-tailed test. If you have a not equals 2 in the alternative like we do here, you're going to have a two-tailed test, two-tailed rejection region. You're going to reject, and that's what it says in the decision rule here. You're basically going to reject if your observed test statistic is quote unquote large enough. Okay, so if the absolute value of T is, in this case, larger than the T critical value, which you look that up in the T table. And for this situation, it's if T is larger than 3.25, or if T is smaller than negative 3.25, or equivalently, if the absolute value of t is greater than 3.25, you're going to reject the null hypothesis and accept the alternative. Step 3. Number 4 there. If you want to think of what does the rejection region kind of mean, it would almost be like if I told, going back to the coin example, if I told you that this coin was fair and I flipped it several times and I got heads in a row, at some point you're going to need to come up with a number at which you're going to reject the assertion that the coin is fair. And so you may come up with a number at 6 or 7 or 8. And so in a sense, that's kind of like what the rejection region is like. It's saying, okay, at what point are we going to doubt the assumption? We're going to outright reject the statement of the null hypothesis. Step 4, here we check the assumptions. I've kind of talked through that a little bit. The test statistic in 2 is valid because we have a random sample, sigma is unknown, and the normality assumption of the underlying population is defendable because the QQ plot looked fairly linear. Descriptive statistics, we didn't compute any here. We let JMP do the work, and so we just need really X bar S in the sample size, and then we plug in that into the ratio to get that T observed test statistic. And then from there, we make a decision. So this test statistic is -1. It's not in the rejection region. It's not terribly unlikely to get something more extreme than this. And so we're going to fail to reject the null hypothesis in this situation. Now, I want to be clear here in step 5. I've made a decision. That's that first sentence there. It's just kind of a mechanical statement. And then the second sentence under step 5 is the interpretation. It goes back to the original question of interest. Can we conclude that the mean diameter is not ½ inch? So going back to that question of interest, well, we don't have sufficient evidence to conclude that the average diameter of all ball bearings is not ½ inch. So it's kind of like it's really more of an inconclusive result than anything. We don't have a proof that H0 is true, but again, we don't have strong evidence that it's not true, and so that's an artifact of the way the hypothesis test philosophy is set up. So that example there. Any other questions with this example? Let's see here. This is another example, and I'll just kind of ask if there's any questions with this example. By the way, I posted in JMP a video, or posted on D2L a video on how to get a hypothesis test and a confidence interval for a population mean in JMP. Okay, any questions with page 22? Page 23 deals with the power of the test. Basically, if you did know the true value of the parameter, what's the chance of you rejecting the false null hypothesis? That's what this computation deals with here. And then that more or less wraps up all that was required through Module 4 for this week. Any other questions with Module 4? Do we want to look at WebAssign stuff?
Yes, please.
Okay, so let's see. I'm gonna try to. Okay, so here is the particular WebAssign that I've got. You may have different, for some of the problems you may have different numbers, but we'll go with what's being projected here. What questions do we have? Where do we need to start?
This is Anna. I was having trouble with number 4 after I determined the lower bound and the upper bound. I got that part right. But then when it came down to, and this was kind of, I guess, linked with my question earlier, finding the t value and the p value.
Okay. All right. So did you, so you got the confidence interval okay. What did you get? Well, you may not have the same data that I've got here.
Oh, I got 4.61 and 5.27.
Okay. Was this the data you had? Was that the same sample mean?
Let me see.
And standard?
Hold up. I think the sample mean was good. Yeah. And standard 0.47 was my sample. So instead of 0.46, it was 0.47.
Okay. Okay. So slightly different. Anyway, so you had a confidence interval. Did it contain the value 5? Let me back up. Tell me what you got again.
Yes, it was the lower bound was 4.61 and the upper bound was 5.27. So it does contain the 5.
It does contain the 5. And so what part B is getting at here, basically it says, just using the interval, does it appear that the oxygen level or that the average level is less than 5? And well, because 5 is contained in this interval, 5 is a plausible value based on this interval. So it's really not evidence at this point that it is less than 5. So I think you probably got no for that.
Yeah. And I think I might have gotten tripped up on that one too, because it was in between, because it goes below 5. But I guess the thing is we can't say it with absolute certainty.
Right. And so if you had a situation, suppose you had an interval, suppose it was say 2, 4.1. We would interpret this as we're 95% confident that mu is between 2 and 4.1. So that says, plausible values are in this range. Now 5 is not in this range, and so now if we got this kind of interval, I might say, yeah.
Okay.
And on the other hand, if the interval say was 6 to 10, we might say, well, there's evidence that the mean is greater than 5.
Okay.
In fact, there's evidence that the mean is greater than 5.9.
Right.
Okay. So anyway, so with part C here, so your hypotheses, let's see. So we're testing, that's the alternative is less than, is that right? That's the claim we want to test, and the null is greater than or equal to. That's what would go in the blank. It would be written like this: mu is H naught would be that mu is greater than or equal to 5. And
I think I got them backwards.
Okay.
Is what happened for me.
So the question here is, can we conclude that the average is less than 5? So you put that in the alternative.
Oh, okay. I was still reading the top part where it says at least 5.0. So in my mind, that was less than or equal to, but I wasn't reading the right part of the problem.
Okay. So that's the setup of the two hypotheses. The T statistic here, you're going to use this formula.
Right.
Okay. So what did you get for that?
Let me see. I'm pulling it up on my browser here because I've got WebAssign. I got negative 0.36, but that was wrong, I can assure you.
Negative 0.36. Okay, so
I did 4.94 minus 5
right.
over
Right.
0.47 over the square root of 8.
Okay. Now, when you do I recommend, I mean, you can do it in one step in your calculator, but I would do the numerator first. It looks like you have it set up right.
Mm-hmm.
Just maybe there was an error in the calculation. So you would have negative 0.06, right?
Uh-huh. Yep, I have that.
Divided by the denominator would be 0.47 divided by the square root of 8, and I get 0.16617.
Okay. Yep, I got that too.
Okay, so if you now divide negative 0.06 by 0.16617, you get negative 0.36, which may have been what you had, but was just the decimal moved into.
Yeah.
I can't remember what you said.
I did negative 0.36. Maybe it didn't like that I threw the 0 in.
Oh, so you had a 0 then 0.36?
But still negative, yes, sir.
Huh.
And well, I'll try it. At least I know. I was just confused because I was like, I know I did that right. But I'll try it, just the negative 0.36. Maybe that'll change something.
Yeah. Try that. Let's see.
It's still telling me I got it wrong for some reason.
Let's see. So the mean you had was 4.94?
Yes.
And that minus 5 is negative 0.06.
Mm-hmm.
Divided by positive 0.47. Then you can multiply that by the square root of 8. So I got negative 0.361. Huh. Is anybody getting something else? Anna, I don't know what the deal is with that.
I think WebAssign's got a vendetta against me.
Yeah.
Yeah, I'm looking at these numbers and I don't know.
Let's see. Hang on a second. There is 8 data points.
Mm-hmm.
I think WebAssign just has it wrong.
Okay.
I tell you what, as a reminder, will you send me an email to D2L
Sure.
for what what you have the answer, what your answer is, just so I can, and I think I can see your answer within your WebAssign submission, but send me an email so I have that reminder so I can go and adjust that.
Sure. Thanks for your help. I just wanted to make sure it was.
Yeah, I'm sorry. I know that's frustrating. Whenever I'm going to let the publisher know about that.
Okay.
So let's talk through the p-value. It sounds like that's what you wanted to do as well.
Yeah.
So in this setting, the p-value would be the probability that t is less than what was observed. In this case, negative 0.36.
I got that.
Okay, so if you want to think about a picture, what that looks like, that is, here's the t distribution. Okay, so over here somewhere is negative 0.36. I'm looking at the area under the curve to the left of that value. That's that probability. Now, you may think, well, I'll go to table N to find that. Well, we've got to use the t table here. Now, the thing in this setting, we need to know the degrees of freedom. The degrees of freedom is going to be 7, right? So I've got degrees of freedom 7, and I'm looking at kind of in the left tail. When I think about what table T gives me, it gives us upper T percentiles.
Okay.
So I might have to couch this in terms of a right tail probability, because the T distribution is symmetric about 0. The area under the curve to the left of negative 0.36 is the same as the area under the curve to the right of positive 0.3.
Okay.
The area under the curve to the left of negative 0.36 is the same as the area under the curve to the right of positive 0.36. So I'm going to go to the T distribution table. Let's see here. So degrees of freedom was 7, right?
Yes.
Now, if I look here, the two values I've got 0.263 and 0.711, and really the observed statistic is between those two, right?
Mm-hmm.
The 0.36 is. So, but I want to take note here that the 0.263 has a right tail probability of 0.40. The 0.711 has a right tail probability of 0.25. Okay, so let's see if we can remember that. So somewhere over here, I've already forgotten the numbers.
0.711.
0.711, and then 0.20. What was the other one?
Let me see. Oh, my book logged me out.
Let's see here.
Sorry, my book logged me out.
Okay, let's see.
0.263, is that what that says?
263. So here is 0.263. Now, what these values are, if I can use that subscript notation that goes along with percentiles, this is T sub 0.20, and this is T sub 0.40. I think that's right. Let me double check. Yeah, 0.263 is T sub 0.40. It has a right probability of 0.40. 711 has a right tail probability of 0.25, so I need to change that. This is not 0.20, but that's 0.2. Let's see here. 0.25, and this was T, so 0.40. So the reason I set this picture up is, and if I use a different color, the area under the curve to the right of 0.70 is 0.25. The area under the curve to the right of 0.263 is 0.40. And so what this tells me is that original black shaded region, which is the p-value, this tells me that, hey, the p-value is between those two numbers. It's between 0.25 and 0.40. Does that picture make sense with that?
Yes.
Okay. So now that's the best we can do from the table we have, that the p-value is between those two numbers. But I'm noticing here that WebAssign is not asking you to put a bound on the p-value. It's not asking you to say what two values the p-value might be between, but it's asking you what is an actual number for it. And this is where I would just say you would want to go to JMP and find the p-value computation. So if you go to JMP, type in the data that you have, the 8 data points, and then go through you'll go through distribution, analyze distribution, and then you can run the test there and get the p-value for that. For details in JMP, watch the video that was recently posted. That's going to help you get that probability.
Okay.
Another way is basically to get a t-distribution calculator, which the table we have basically gives t probabilities for certain t values, but you can actually get exact probabilities for a t-distribution with a t calculator. Those are online. If you just Googled t-calculator, StatTrek is a group that puts out a t-calculator that's really good.
Okay.
And it'll ask for the degrees of freedom. You plug that in, then you plug in negative 0.36, and it should give you a p-value.
Okay, great. Thank you.
Okay, and I think what we'll see, I mean, to answer this last question, we don't even need to know the p-value exactly. The p-value is pretty large, right?
Mm-hmm.
It's bigger than 0.25, so it's not smaller than the significance level chosen. So we would fail to reject the null, right? So it's going to be either option B or C. We're going to fail to reject the null and conclude that the data, let's see, what would we go with? That the data
not support.
Right.
Okay. That the mean is less than 5.
Right. So it would be this third option here.
Okay.
For what we're getting.
Okay. Thank you.
Mm-hmm. Other WebAssign questions?
So for testing purposes, like the way WebAssign asked that question, like you might ask us like the bounds of a p-value, but not what the p-value is.
Right. Yeah.
Okay.
Or I might, or because if you only have that table in front of you, that's the best you can do. I might present some JMP output and ask you what the p-value is, and make a decision from the JMP output. But that would actually be easier than putting a bound on it, because JMP will automatically, it gives you the p-value. You just got to go find it in the output. Now, what I could do on a problem like this, maybe instead of asking you to compute the p-value, I might ask you to tell me the rejection region or the decision rule of the test, which is something that we've kind of worked through on some other examples. Okay, next WebAssign question. We can go before 4 or 5 and so forth.
I had a question on number 6.
Okay.
I was kind of the same way with Anna before. I got the T on 6A. I got the T value right, but I couldn't get the P value, but I got it down to in between 2 numbers. So I guess that's that. But then on B, I guess it kind of threw me off when it said.
Do y'all want me to show? I'm sorry to interrupt. Do you want me to show you that T calculator online?
Yes. Because I have not been able to get JMP downloaded onto my computer. I still can't figure it out. I had my husband try to help me, and.
Okay.
So.
Let's try to. Did you try to call anybody on the SFA campus?
No, I haven't. Well, I need to get him to help me after you gave us the new PER file or whatever. So maybe I can figure it out with that.
Okay. So I'm going to Google StatTrak T distribution calculator. Anyway, this is kind of a neat website. It has a lot of, so the degrees of freedom, what is the degrees of freedom here? I'm not looking at the problem.
It would be, well, there's, so it'd be 9. There's 10 data points, so it's 9.
Okay. So you got it. What was your what T-score did you get?
0.87.
Okay. So then what you do is you calculate, and there you see it says the probability that T is less than 0.87 is 0.7965.
Okay.
And so that's not necessarily the p-value. You got to go back and look at your test to see, is this a right tail test? Is this a left tail test? Am I going to, when you draw your picture of the p-value, is it going to look like, I'm going back here to this problem we were looking at before. Is it going to look like, is it an area under the curve to the left or to the right that I ultimately need? And so I'm thinking about number 6.
I have the, so the,
or is it a two-tail test? I didn't even think about that.
Well, the mu after, in the top part of the question, the mu after.
So the alternative was greater than?
Yes.
Okay.
Yeah.
Yeah.
Like
so
that.
Has there been a significant gain? Yeah. So that's going to be a right tail test. So if, thinking about the p-value, what did you get again? 0.7?
0.8. The T value is 0.87.
Okay, but what was that was the test statistic you computed?
Oh, okay. The P value is 0.7965.
Okay, so
the one we just calculated on that other thing.
Yeah. So remind me, what did you get for your observed test statistic?
Hold on. Let me see. I think that's 0.87, right? Is that the T?
0.87.
Yeah.
Oh, Okay, so
minus 0 over 7.54 divided by the square root of 10.
So 2.11 minus 0. Okay. So what that calculator online gave us, the probability that t was less than or equal to 0.87, it told us what that number was. What was that?
0.7965.
Okay. So 7965. When I think about I'm going to come back to this picture here. My observed test statistic, or that y'all got, was 0.87. Because it's a right tail test, this area under here, that's the p-value that we want. But the probability that's given by that table is, because this is less than, it's the area under the curve to the left of 0.87. So this area here is 0.77965. So the actual p-value would be 1 minus 0.7965.
.2035.
Okay.
Yeah. I mean, yes, that makes sense.
Okay.
I'll try it and put it in there. And then on the, well, I didn't even look at the little circle ones yet, but so on the bottom, on B, I got confused because it said construct a 90% confidence interval, but then in the parentheses it says note that the two-sided 90% confidence interval corresponds to a one-tailed 0.05 test. So I guess I got confused about that multiplier there. You know what the t sub alpha divided by 2 translates to, I guess.
Right. Let me address. I'll address that. Let me say this t value here. That in part A, you might want to go recheck your calculation. I know I wrote down 0.87 there, but I think you should be getting 0.8849 or 885 for that
Okay.
test statistic. Because I just did 2.11 minus 0, and I described some of that process. Did y'all see that in that PDF document?
Yes.
Yeah. Okay. So I described that process in that PDF document, but so anyway, double check that. So okay, so back to this part B here. Can I call this this row D for difference? And basically here we're doing D bar plus or minus T sub alpha over 2 times the standard deviation of my differences divided by the square root of n. Is that okay?
Yes.
So instead of using X or Y, because we've taken the differences, the after minus the before, that's what we're doing inference on. You could call it mu sub D. I think in that PDF I called it mu sub change. But we want to estimate that parameter with this confidence interval. So yes, so you take 2.11 plus or minus. Yeah, we're going to have to figure that out. SD here is at 7.54, right?
Yes.
Square root of n is 10. This T multiplier. So still, we have a 90% confidence level. So that means alpha is going to be 1 minus 0.90 or 10%. Right?
Right.
So the T value I'm going to have t with a subscript of 0.10 divided by 2, which is t, so 0.05. All right, but I've got to have the right degrees of freedom. Again, the degrees of freedom here is 9. I get this from the t-distribution table. Okay, let's see if we can find it here. Here is the t-distribution table. Degrees of freedom is 9. Is it 1.833? Is that right?
That's what I was going to guess.
Okay.
So 9 corresponds with the 0.05.
1.833. Say that again.
Oh, nothing.
So this parenthetical statement in here is they're saying, and they're making a note that statement, and it's the rationale behind it. I'm not going to get into, but they're just saying, hey, if you want to perform a one-sided hypothesis test where alpha is 0.05, one way to do that is to compute the two-sided confidence interval, but you have to do 1 minus 2 times 0.05. In other words, you got to do 1 minus 2 times 0.05, which is that's going to be 1 minus 0.10, or a 90% confidence interval. That note there is they're just trying to get you to see, to draw a connection between computing a confidence interval, using that to make it, and using that confidence interval to make a decision about a hypothesis test. And so the interval here, what did y'all get for that? Did anybody get that? Negative 2.26 for a lower bound? Maybe? Anybody get that?
Well, I was using the wrong, I guess you call it T multiplier, because I got confused with the whole alpha equals 0.05. So, but I understand what to do now. So I'm trying to.
Okay. So then here, what you're going to do is, whatever this turns out to be, you're going to check to see is 0 in this interval. And if 0 is in the interval, that's going to be evidence. That's not going to be. That's going to lead you to fail to reject the null hypothesis here, because if you look in that PDF document, mu d, the mean difference, is the same as mu after. I don't like the way I'm writing that. If we want to think of mu after is less than or equal to mu before, one way an alternative way to write that is if mu after minus mu before is less than or equal to 0. Right? Maybe I shouldn't use alternative. I should say an equivalent way is to look at the difference between the two. And so the thing that I want us to note is that we basically need to check to see if 0 is in the interval on mu change, which is mu after minus mu before, or mu d, whatever you want to call it. Does our interval contain 0? If it does contain 0, then the null hypothesis value for mu change is plausible, so that would be a failure of rejecting the null hypothesis. But if you think about the alternative, is that mu after is greater than mu before, mu after minus mu before, that's equivalent to the difference, this difference here being positive. So if you had a confidence interval where everything was positive in it, say the interval 3 to 5, that would be evidence to cause you to reject the null and accept the alternative. See how the 3 to 5 would coincide with this sort of statement about the difference of the average difference for that population. So anyway, that should give you some insight into dealing with that last bit.
Yes, that helps.
Other
Thank
questions? Okay, good. Other questions with WebAssign? All right. We're about at 8:30, but if there's another question, we can address it. Other questions with this module? Okay, so next Thursday is the exam, right? And excuse me. So next Thursday is the exam. In terms of preparing for the exam, I would recommend that you can work all the WebAssign problems, that you can work all the practice problems, that you can work all the examples in the notes. That would be the place that I would recommend that you start in studying for the exam. And all the while, there's concepts that are throughout your notes that might be addressed on the exam. And so you may want to have kind of two things running at once, where you're working a bunch of problems and one set of papers, and then another set of papers you're kind of thinking through and writing out and making sure you have all the concepts squared away. In terms of conceptual things, you might want to have an outline for it, starting with, of course, Module 1 and Module 2 and so forth. And then from each of those conceptual part, each of the concepts, try to link it to a problem that you see in the homework, or that you see in the notes, or that you see on the practice problems. And that'll help connect, that'll help solidify your understanding of the concepts, and also, I think also help working the problems as well. Let me say one thing about this course. I know this is, for many in this class, statistics this may be the first and last stat course you take in graduate school. And you think, why do I have to take it? I was talking with Dr. Bray last week, and about the idea that, I'm trying to get to the front of this book. I don't know how to do that. Let's see. About what do we really want? What are the objectives we want for a student to have after this course? It's not so much to become a statistician or to become real proficient in JMP, this sort of thing, but in this intended audience, I think it hits the nail on the head here. This course provides a broad overview for methods for advanced undergraduate or graduate students from a variety of disciplines, and this book is intended to prepare students to solve problems encountered in research projects, which I may see that later in your in curriculum, to make decisions based on data in general settings, both within and beyond the university setting. And finally, and this is kind of, I think, really most important as you go on and you have a career that's not, that doesn't focus on statistical analysis, but finally become critical readers of statistical analyses in research papers and in news reports. As you look at articles within your discipline, whether it's nursing or biology or ag, there's a good chance that they're going to be using statistics at some point, and you're going to have some proficiency in understanding some basic statistics to get the gist of the article, to really put some scrutiny to the article with the findings of the article. Do they have a reasonable statistical approach to conclude that drug A is better than drug B, or to conclude that fertilizer A is better than fertilizer B? So anyway, I want to say that just as a kind of a broad statement about the course, and I think that's kind of what the nursing faculty are looking for as well. And I would say that would be pretty similar for disciplines, not just nursing, but any applied discipline that would use statistics in an applied way. Okay, so that wraps up our Zoom session for week 5. Any other questions? All right. Well, we'll call it a night, and I hope y'all have a good weekend. And if you have some lingering questions this evening or into tomorrow, feel free to email me, and I'll try to respond to those. Email me early in the morning. I say early, but earlier in the morning as opposed to later in the afternoon or early evening. I'm not going to get to it by that point. So the emails need to get to my inbox pretty quickly for me to respond before the weekend gets here. Okay. Well, y'all have a good night, and I will talk to y'all later.
Bye. Thank you.
You bet.